All right, ladies and gentlemen, we're going to continue our discussion of Lewis structures and bonding. So we started with this example here. We've got our lovely molecule here, and part B is to label each bond in the molecule. We did the precursor to this question last week when we asked ourselves, what's the hybridization of this atom? Why do atoms hybridize? To get electrons further away from each other so they can obey the principal tenet of the separ. The valence shell electron pairs repel each other. That's why they have to rehybridize. Atomic orbitals don't have the electrons in the right spatial arrangement. They're not separated as well as they could be in a molecule. And what were the two things you had to count for an atom to determine its hybridization? Lone pairs, sigma bonds only, right? Don't count anything else. So we'll be doing that for every atom in this molecule except for the hydrogens, because hydrogens don't hybridize. Hybridization means mixing together of things. And hydrogen only has the s orbital. How can you mix one thing? You can't. One thing. So hydrogen, when it makes a bond, it only uses the orbital it's got. What is the orbital that hydrogen has? The s, and it's the smallest possible s. So what else is that s called? The 1s. But you can call it s. I like s. That's fine. You don't have to tell me which row it's in. Okay. So label each bond in the molecule. So guys, you're going to have the same label for many bonds in a molecule. Please don't write that label over and over and over again. Time's money, remember? Come up with a symbol for that label. Say the number 1 or the letter A or whatever symbol you prefer. I have one student just use, they love the icon. So happy face with 4 eyes, happy face with the bent nose. I don't they put happy faces for everything, and it was harder to grade, but you know, I admired their use of the happy face. So I prefer numbers or letters, seriously. But here we go. So I'm just going to label. I got to label every single bond in this thing. It's got to happen. If there's a bond and you don't tell me what it is, you're going to lose some points. So let's start on the left. And you'll notice every time on an exam, when you look at an answer key, I like taking care of the ones that have a hydrogen bonded to something first, just to get them out of the way, and then move on from there. It's just a personal preference. There's no right order here, okay? So everything with an H on it attached to an sp2 atom gets the label 1. And because this is going to get a little more cluttered, I can do something you can't do. I can copy paste. You can't do that on a test. But I'm just going to copy this whole thing and put it lower so we can see the progression of this question better. And I think somebody had a question, though. No. There'll be some erasing involved here. Maybe. Come on. There it is. So please don't you copy it. No. You just get it all on the one molecule. That thing did not want to erase, did it? That's weird. Okay. I bet it disappears later. Dude. That's trying to move the thing up a little. That's all. There. I'm going to call this labels in baby blue. No, it doesn't show up right. 1, orange. 1. Are there any H's bonded to sp2 atoms? Yeah. Don't say that this is the same bond here. And just to be clear, I'm going to circle my numbers. This, do not call this 1. I'm going to call it 2. Why does it have to have a different label? The carbon attached to that H is sp3. You know how I know that? 4 sigma bonds. The carbon on the left here is sp2. How come? 3 sigma bonds. No lone pairs. 3. 3 is the number. sp2.
There's another name for the sigma bond, for the lone pair is K maybe?
No, we're not going to name lone pairs. You may have seen that somewhere else, but we're not going to do that.
Okay, but I just want to remember the letters for these A.
Well, these are letters of my choosing, so there's no standard process here.
Okay.
So I'm going to go 1 here. Why? Because both of those carbons are what hybridization? sp2. And then these are 2s, aren't they? I put a 1 by mistake. That's sp3 carbon, right? Maybe I should write down what 1 stands for before I keep yammering on. The labeling always goes like this. 1, what type of bond is it? You only have 2 choices, sigma or pi. You need one of those letters in front. If it's the only bond between 2 atoms, you know which one that is, right? What do you write down? Uh-oh. You have 2 choices, sigma or pi. There's only 1 bond between the C and the H. Sigma. Sigma. How do you write a sigma? Tell me. Do not write the letter S. I will have to dock you maybe a quarter point. It's like a eyeball with a lash on it to the right. Draw a circle with an eyelash to the right. There you go, sigma. That's how you write sigma. Okay? And you need to name the orbital from atom number 1 that's being used to make the bond, and the orbital from atom number 2 that's being used to make the bond. So we just went through this. When hydrogen makes a bond, what orbital does it use every time? S. It has no other orbitals to mix with that. So both 1 and 2 are going to start with S, because they both have a S orbital on hydrogen overlapping with another orbital to make this sigma orbital. It's a new orbital when they overlap. It's called a sigma bond after you're finished. So the carbon that's in red, what's its hybridization? sp2. It uses that orbital to overlap with the s orbital of hydrogen to make a sigma bond called sigma, S-sp2. So every label number 1 will be an s orbital bonded to an sp2 hybrid, and the new thing is called a sigma bond, and it's an orbital. It's a molecular orbital now. And that's its new name. It's named after from whence it came, right? It's sort of like the prefix bin in Arabic, or muk in Scottish. McDonald, son of Donald, right? Same for bin, right? So we're naming it after the pieces it came from. And what is about, what is the hybridization of the carbon when the label is a 2? sp3. So why is this important? Well, I'm going to tell you right off that number 1 is a slightly stronger bond than number 2 based on only hybridization. And the great question now would be, why? Right? Well, think about it. I'm taking you back to Chem 141. You learned how to fill out atomic orbitals for atoms, right? You always filled out the S first. Why? There's only one reason. You filled out one orbital before the next one. Why was it more stable? I like your answer. Less potential energy. I like what you're saying. Is another way of saying less reactive. Is you good? It's synonymous. Less reactive, more stable. Did I say more stable and you didn't say? I think that's what I was looking for. More stable. Closest one of the nucleus is what I was really looking for. We always put, hey, your electrons, there's only one thing in the universe you like. What is it? What is the only thing an electron likes?
Energy. No, atoms.
You're going to make me sing some Paula Abdul now? Don't make me do that.
Let's have
No, we're talking electrons only. There's only one thing an electron is interested in getting close to. One thing. I want a one-word answer. The electrons hate electrons. Proton! Okay. Now this goes with the answer she gave me. Where do you put the electron first?
Closer to the proton.
Closer to the proton, but how did she say it? Closer to the nucleus. You just said the same thing, right? So, yeah. So electrons want to get close to the nucleus. Well, you keep putting them closest to the nucleus, and then another electron in the same orbital, and then that orbital's full. You can't put electrons in there. Now electrons start hating on each other and say, no, no more. This booking is full. Okay. Next, and you go next closest to the nucleus, right? We have a question.
Does like protons have like attraction towards the electron?
That's why this whole discussion's happening, because protons have attraction to electrons. That's the only attraction in the normal chemistry we ever talk about. And we talk about the electrons that are accessible in a molecule. We call those valence electrons, right? And yeah. So the reason why number 1 is stronger than number 2 is because if you're an sp2 hybrid, you were made from 3 pieces, one called an S, 2 called P. And if you're an sp3 hybrid, you were made from 4 pieces, one called S, 3 called P. And you already told me which orbital is closer to the nucleus, S or P. Which one? S. So which hybrid is closer to the nucleus? One that is 33% S. That's 1 part S for 3 parts total. SPP, 33% S. Or a 25% S for an sp3 hybrid. SPPP. Which one's closer to the nucleus? 25% S or 33% S? 33% S. It's more like an S orbital. Well, do you think this is important? Of course it is. Helps us predict which bonds are stronger and weaker. Yeah. Let's finish up our 2s and our 1s. That's a 1 because it's sp2. That's a 1 because it's sp2. We got a bunch of sp3s. How come that oxygen's sp3? That one on the bottom, purple. 2 lone pairs, 2 sigma bonds. That's 4 fingers. That's sp3. Same for this for different reasons, because 4 sigma. 2, 2, 2. 2, 2, 2. A lot of 2s, huh? A lot of 2s. Okay, and then I'm just going to go from the left to the right until my molecule's done. I've done all the CHs, right? Yeah. So we're going to do a 3, and we'll do it in baby blue. This bond here. I kind of wrote it right on the bond. So tell me what kind of bond it is, sigma or pi? It's the only bond, so it's a sigma. And what's the hybridization on the carbon on the left? We already talked about sp2. And what's the hybridization of the carbon on the right? sp3. And I'm going to do it this way because the question, I know it's coming anyway. I'm going to write sp3-sp2, and somebody's going to say, wait, it's not that. You just said it was sp2-sp3. Molecules don't know direction. You can go left to right or right to left. Okay? So anytime I have an sp3 bonded to an sp2 with a sigma bond, I'm going to put label 3. And I got one right here. How do I know that? The carbon to the left is sp3, 4 sigma bonds. Carbon to the right, 3 sigma bonds, no lone pair, sp2. What about this one? Why is oxygen sp3? Tell me. I'm going to have 4 fingers up when I'm done. 2 lone pairs, 2 sigmas. And why is the carbon in green sp2? Well, it's got 3 sigmas. And any more 3s? We got sp3, sp2. We got oh yeah. And oh yeah. The carbon between those 2 number 3s is sp3, and the carbon on the outside, each one sp2.
So it doesn't matter where you start?
Doesn't matter where I start. As long as one of the atoms is sp3 and the other is sp2, then it's got the same label. sp3, sp2. Cool. sp3 for O, sp2 for carbon. And I believe that's the end of that label. And then 4 is keep going, left to right until every bond gets labeled. I got an sp3 carbon underneath and an sp3 oxygen up top. Let's write that down. Yeah. And I got that here as well. And here as well. Here as well. Here as well. Oh yeah, look at those consecutive. That's a record. 1, 2, 3, 4 consecutive bonds. And here. And here. And here. And here. We're getting there, aren't we? We're gonna have a bunch of 5s. I'm gonna call this 5. That first bond between the C and the O. What kind of bond is it? The first bond between the C and the O. Sigma. The first bond is always a sigma. The carbon in red, what hybridization? Far left of the molecule, carbon in red. sp2, it's got 3 sigmas. The oxygen above, and I want to know why. Also sp2, it's got the red oxygen's got 1 sigma bond and 2 lone pairs. Okay, and you better write sp2 for that too. And let's finish up some more 5s. That's a 5 right there. This here is not a 5 because the carbon to the right is sp. The 2 black bonds are the sigmas. There's only 2 sigmas. Yeah. And similarly, that's sp to sp. Well, that's sp2 to sp. That's no good. That's sp2 to sp2. That's good. I'm going to sneak a 5 in there. Yeah. And that's the last one for those.
How can you grade it when
This page takes an hour for me to grade on the exam. I just go over your labels and make sure you correctly label them. Yep. Been doing it for years. You get better at it. And yeah, I'm not going to do the pie. You know why I'm not going to do the pie? This is the comic relief section of today's lecture. I saved pie for dessert. That's why I'm not going to do pie. I'm going to do the pies at the end. Okay, let's do all the sigmas. I think I need a 6 for that one and that one, and that's the only 2 6s. Once again, we're doing sigmas first. Sigma. Carbon on the left of the first label 6 is sp2. Carbon on the right is sp. The sigmas are all in black in those 2 carbons. And I think that's the only unique number 6, and there's only one number 7. Each carbon is sp there. Of all the sigma bonds, that 7 will definitely be the strongest of all the sigma bonds. If you look at it, there's 4 parts in the name, sp, sp, right? Half of those are s, the 2 s's, and half of them are, that's 50% s. Those are strong sigma bonds. Number 7. Sigma done yet? I think the sigmas are done. Somebody will correct me if I missed something. Pi. We'll go pi in, I don't know, purple. We'll call this one number 8. We'll call this one number 8. I cannot call the next one number 8. We'll talk about that in a second, but I can call this one number 8. What? I'm going to call all my pies 8 except for the 1. And you better label it. First of all, you know it's not a sigma bond because you've labeled the sigma bonds already and they're taken care of. You can't use the sigma anymore. What's the next bond called? Pi. What types of orbitals are used to make pi? P. P makes pi. All right. Remember, for orbitals to make a bond, they have to overlap. Here is a p orbital. Here's another p orbital. If they overlap, they make a pi bond. See them overlapping? They're no longer p orbitals. They're called a pi bond. It's not called p anymore. You used a p, you used another p that had the same orientation. Because if you used a p that had a different orientation, like py and pz, did they overlap at all? Can't make a bond that way. You can use py, or you could use pz, or you could use px. They all form an overlap. So you have to show me you know all those things. One, you make pi bonds from p orbitals. That's the easiest thing to show. You write the letter p and another letter p. One of the atoms provides a p orbital and so does the other. And I can't give you full credit here because you haven't showed me that you know the orbitals must align with each other. They must have the same orientation. And you pick one of the three letters for both. That's how simple that is. X, Y, or Z. So if you make this one using py, then you've made your pi. Now the reason why I didn't label this one with a number 8 is because I know, and you're supposed to know, that you can only use an orbital once. If you've used an orbital to make a pi bond, you can't use it to make a different pi bond in a different direction. So this carbon on the left, sorry, we're talking about this bond here, right? This carbon on the left of this bond has already used its py orbital to make a pi bond to this carbon. You already told me that. You can't use the same py orbital to make a pi bond to this. You must pick a new one. Pick any new one that is not py. 9.
How many are there usually on like?
This is a typical length question for this exam.
How many points?
It's about 20. The labeling part is about 7 more points, 6 or 7, and the drawing the structure itself was already 5. So you're up to 13, sorry.
So how many questions?
And then 1. And then at the end, you got to do the bonding geometry with both the angles and the name. That's 6 more points or 5 more. I'm ballparking here. We're up to 17 or 18. Then functional groups gets you over 20. It is a 20-point question. Do not skip this question. Not a good strategy there. Did we get every bond? I think we did. All right. What do you think? Make it a triple video? And 3 participation points? I think it's a great idea. Thanks. Okay.